Welcome to my talk about evolutionary architecture. And when we develop software nowadays, I hope we do it something like this here. So we have a team, a product team that develops the software product and ships it to its users and customers. And we should deliver it frequently and often to get as much feedback as early as possible. Because, as is its most cases, we aren't the users of our system. So in my case, I'm a user of my own system, but normally we aren't. And so we don't understand our users really well. So we need their feedback to improve our product. And we should deliver something, show it, get the feedback, and then we should be able to react to that feedback. It doesn't help much if you get great feedback and the developer team says, yeah, that would be a great idea, but we can't do that in our system. It's not possible anymore. And one key point is we should focus on learning. We as software developers should learn about the needs and the problems our users have so that we can provide a software that helps them in their daily lives. And that's a problem for a software architect or for any developer who thinks about architectural decisions because we don't know what the feedback will be. So when I learned about software architecture at university over 20 years ago, it was very simple. Look at the problem, think a little bit, design a solution and let the developers implement it. Done. Yeah, but you all know that doesn't work this way. There is feedback, and the feedback may be, yeah, you have a nice system, but it's a little bit slow. Could you make it faster? Then you tweak some index in the database, and then, yeah, we have to change the architecture. So, as a software architect, I want the architecture of our system to evolve together with the rest of the system, with the functionality. And I mean by evolutionary that the software architecture is fit for what we need today and doesn't provide anything more because it would be over complex. But it should be open to be changed for the needs that come tomorrow, next week, next month, in 5 years. I don't know about 10 years, that's probably too far away. So I have two principles. Principle one is I want to act in the short term. So I want that the architecture supports what we do now, maybe the next couple of weeks. But only that, I don't want to invest more, but it should be in a way that we can add to the architecture, we can change the architecture to enable future feature implementations. What I mean by that, I have an example. I work for a company that builds an attendance time tracking tool. Yeah, sounds really boring, and it isn't. It's highly complex. And when we started 8 years ago, we wanted to build a new product. So attendance time tracking tool, there are many out there in the market. I'm sure you all have to deal with one in your daily job. And if you want to get a new product into the market, it has to be better than what is already there. Otherwise, nobody will buy it. And to answer the question, can we build something better? Persistence is not really that important. Once you have a system that is live and users are using, yes, we need to persist our data. But to answer the question, can you build a system that anybody would pay money for? It's quite irrelevant. So 8 years ago when we started, we ignored persisting data. We built some business logic, we built some UI, we showed it to potential customers and got the feedback. Yeah, that looks nice. That's much easier than what we have at the moment. So yeah, maybe we could sell that. So we started just with keep the data in memory. Good enough for demos. And after a couple of weeks and months, when he had a working prototype, yeah, I thought, yeah, we get more and more business logic. It's mainly about automating all the things that HR people have to do. We should separate the business logic from how we want to persist the data in the future, because now it's still in memory. So we introduce some interfaces, some functions to get data from the database, to store data back to the database, so that once we will implement that, the business logic doesn't have to change anymore. So we introduce some abstractions. And at some point in time, we said, yes, we want to go live. So we had to implement the persistence. And the nice thing was, at that moment in time, we had a lot of knowledge about the data we have to persist. What's the form of the data, its structure? We could say, what's the data growth per day of this data? And all this knowledge was really helpful in deciding, should we go with a relational database, should we go with document-based, or even key-value or graph-based database? And as boring it is, we went with a relational database with some document-based features in it. And yeah, we had the first customer, we were ourselves. So we had a second customer, a third customer. So scaling really wasn't a problem. So one backend node, one database is really fast enough for 50, 60 users. But nowadays we have a couple of hundred customers, a couple of thousand users, and scaling plays a role now. So we had to decide, do we want to use horizontal scaling, multiple backend nodes, for example, vertical scaling, that's the thing we use for our database. We just take a bigger server, bigger database, and a lot of things we didn't have to scale at all. It's just still the same thing as in the beginning. But again, when we noticed with the telemetry data that things started to get slower, then we reacted and decided which way we want to go. So as you can see, we did the whole path here in many, many steps over, let's say, 5 or 6 years. And we only decided what was necessary at that point in time when we decided it. But what's also very important is we always knew at some point we will have to scale. Because if we want to succeed as a company, we need 25,000 users in our system, paying users. Then it works financially. So when we started, we knew at some point we need to scale. So on the path from top to bottom, we always thought about, if we decide this, does it prevent scaling in the end? So let's say, yes, let's go relational database. And yes, I know this great technology, it's called Access. That would be a bad decision because you can't scale Access above one user. So that would be a dead end. But yeah, we went with SQL Server, and we know SQL Server supports scaling in some way that would allow us to run 25,000 concurrent users, more or less concurrent users. Because attendance time tracking has spikes in its usage because everyone starts at 8 o'clock and everyone goes to lunch at 12 o'clock. And the rest of the day, the system there is almost no load. So we did this in many steps, always with the big picture in mind. And when we started, we didn't do this only for persistence, but for all these aspects that are on this slide. So you can't read it, but you can send me an email and I can send you this slide, or you probably can download it after the conference somewhere. So for the rest of the talk, I'll pick some of these aspects from this slide here. Let's stay with storing data. There are basically two models how you can store data. You can use CRUD, create, read, update, delete. That means you just store the current state of your data in the database, you load it back, you do some business logic with it. And whenever you change the state, you update the data you have in the database. That's CRUD. It's possibly the simplest way to persist data. But maybe a feedback from users would be, yeah, it would be nice if you could see how the data changed over time. Then you say, okay, we could. One way would be CRUD with history. So whenever you change data, you have two options mainly. You can say, okay, I don't overwrite the data. I have an additional column that says it's updated, it's archived, whatever, with a date, and you insert the new data in the same table. Or you have two tables, you copy the old data to the history table and update the existing record in your database. So I may have to make sure that I don't fall from this stage here. Yeah, that's the way when you go with CRUD. On the other side, if history is really, really important, then maybe it's better to go with event sourcing. So instead of just storing the current state, we store all the events, all the deltas from the beginning that led up to the current state. So maybe a customer was created. Then, because they got married, the name was changed, for example. All the events, and if I need the current state, I can replay or project all the events that I have for a certain projection. Many call that entities or aggregates. We call it projection because that's what it is. And with event sourcing, history is always there. You can project up to a certain event and you know what it was at the time. And it's always possible. You think, yeah, we start with event sourcing, but we don't need history. You can always fall back to CRUD because you have all the data. If you have CRUD, you can't switch easily to event sourcing because you have to interpret your data. So if in doubt, maybe it's better to go with event sourcing. And many event streams, an event stream, this is a stream of events in our database. That's all there is. And whenever we need the current state, we just replay, project all the events to get it. So for event streams that are short, no big problem, 10, 20 events, project them, it's really, really fast. But at some point, for some streams, this projection gets too slow. Maybe you have a lot of events in a stream. Maybe the projection of the events is CPU intensive. For example, you have some tree structures, and modifying tree structures takes a little bit of CPU compute. And then we ended up with 3 different possibilities. The first is to introduce snapshot events, the one on the right. That means instead of replaying all the events, at certain times I insert a snapshot event that stands for all the things that happened before. So when I need the current state, I look at what is the last snapshot event and just replay from there. So you shorten the event stream. So if the projection is too CPU heavy, this could be an option. The problem with this approach is when you want to change events in the past, I know real hardcore event sources say that's forbidden. It's like in your Git repository when you have to change something in the past. But sometimes you have to because maybe you had a bug in the system or the users did something they shouldn't do. So from time to time that happens to us. And it's nice we can change events in the past. And when you have a snapshot event, you have to get rid of them first because otherwise the data is wrong. Another option, and I would say that's the classical event sourcing option, is to introduce a read model. So whenever you add an event to the event stream, you also update the current state in the read model. So you have 2 stores, the primary, the events, and the read model, the current state. I think that's what normally is in the literature about event sourcing. And again, here you have 2 options. You can, when you write the event, do it in the same transactions into the read model. You have a consistent way. Or you say, I just write the event, write a message to the boss, please update the read model sometime soon, please. You have an eventual consistent way to deal with these updates. But you have to keep in mind that now you have more data in the database. Maybe that's relevant to your system. And the third option that we use is caching. because we have some really big data structures that we read a lot. And getting them out of the database is already a problem, even from the read model. So you want to keep them in memory, binary in memory. And caching, caching is quite easy until you have to invalidate the cache. So instead of getting the data from the database, you ask the cache, do you have this data? And if the cache says, yes, here you have it, you're finished. Otherwise, you get the data from the database, add it to the cache, return the data. The problem is when things change. So you have to get rid of it in the cache. Otherwise, you have old data. And there are some simple techniques. Size, limit the cache size. The cache can hold, I say something, 100 elements. And when the 101st element comes, you get rid of anyone. The oldest, the one that was least accessed, whatever. Or you have a time constraint. Data can survive 5 minutes, 1 day, whatever suits your use case. Or that what we normally want is when the data changes, we have to invalidate it. But it's really difficult when you have a scaled system, a distributed system, to find all the caches you have to delete exactly what data in there when something happens. That's really difficult. I'm sure you know the joke about the 2 most difficult problems in software development: naming things, cache invalidation, and off-by-1 errors. So, but we do that if it's worth the trouble, because the system gets more performant. And latest edition, not really live yet, but we are working with, I'm a step too far now. Another option is, if you have a distributed system, is to use a distributed cache, like Redis or something. So you have more or less a singleton cache, and you get the data from there. But if the data is hard to serialize or read from a database, it's also hard to read from a distributed cache. And that is too slow in our case, again. So what we ended up with, last evolution step, is a mix of local in-memory cache combined with a distributed cache. So if I need the data, I ask my local cache, do you have the data? If it says no, I have to get it. It gets the data from the database. If it has the data, it says, yes, I have the data, but let me check first if it's up to date. It goes to the distributed cache and gets a token from there. This token is updated whenever the data changes. And updating in the distributed cache is rather simple. It takes the token, compares it to the local token, and if it's the same, it returns the data. Otherwise, the cache knows it's old data, it has to fetch the data from the database. And that speeds things up quite dramatically in one single use case in our system. It also bumps the memory load quite high. So you see, there are a lot of decisions here, a lot of trade-offs. There's not one right way to do it. We decide per use case with which option we want to go, and if the current system has a performance or any problem, we think about how could we evolve with a next step. And again, we try to choose options, we try to make decisions that leave as many options open as possible. So you see, if in doubt, we go with event sourcing, because we just have more options. If we go with CRUD, we know if history comes, CRUD with history is tedious, and if there are more needs coming, we probably hit the dead end. But please don't build a system completely out of this event sourcing. That's surely overkill. Next topic I want to talk about is layering and structure. So as you see, I go through all the hype topics now in this talk here. So when we started 8 years ago, or when you start a new software product, don't think about structure and layering, because you write your first line of code. It's always simple. It doesn't matter how your folder structure look, how your layers look. When you have written a couple of thousand lines of code, then start thinking about structure and layering, because many thousand lines of code it gets hard to navigate the code base. But when you have written a couple of thousand lines of code, then you already know much more about your system and the problem you try to solve than when you started. So maybe you start to see what we call subsystems. If you're a DDD fan, call it bounded context, whatever. Just a box in a box. Yeah, we software architects, we think with boxes in boxes and connect them with lines. Yeah. So you see some candidates for subsystems. You move the code around, you restructure your code base. You see if they have talked too much to each other, then maybe the boundaries aren't that good. You try to find some good subsystems. And then when the subsystems grow again, because you added more and more code, you can think about layering. Maybe going with hexagonal architecture is good enough. You have some incoming adapters, you have some outgoing adapters, but the rest is just one big box. And then the system grows and grows. So yeah, some additional layers, differentiating between core models and application services would benefit us. Then maybe go with onion architecture or clean architecture. And if things grow and grow and you have multiple teams suddenly, maybe you can think about microservices. But please don't start with microservices when you only have 10 lines of code. And if things still grow and grow, at some point you have to think about modularization inside these layers. How you can make things smaller that you can understand them in your head, because we can keep 5 to 7 things in our working memory at any given time. So code, functions, modules should be quite small. But start with one box. If the box gets too big, make smaller boxes. And so you can evolve the structure over many years of your system. Then scaling. So I had a flu last week, so I have to make sure that my voice is good enough for the next 20 minutes. Again, when we start, you have some business logic that you want to code. It's probably easiest to start single-threaded. Just make it pass the test in a single-threaded way. And you also have to know that single-threaded code can be really, really fast code, because as long as you know you're single-threaded, you don't need locks, you don't need semaphores. These things are slow. So single-threaded code can be really, really fast. If you want to parallelize, don't go to 2 instances, probably go to 20, and then you have a gain again. And between that, just doesn't make sense, because communication overhead kills any performance. And again, but when you start single-threaded, you can do it in a way that you make the next step easier to go multi-threaded, and that is use immutable data, because you can share immutable data with everyone. It's not a big problem in a multi-threaded system. Problems in multi-threaded systems are always mutable shared state, not immutable shared state. And the other thing is, if you can use pure functions, that means use code that, as long as you put in the same arguments, you get out the same result. So you don't get data from the database or write to a file. Makes easier to scale such things. And then, before you start multi-threading, maybe you can scale vertically, take a faster machine. And we see that in our system. We are on Azure, and every year you get faster hardware. So we get more users every year, but we can just move the slider a little bit. Yes, I need a CPU more. And up to now, it works great. So a lot of things we can't scale vertically. It's much easier. At some point, it gets too expensive, so we have to change to horizontal scaling, and then we can go multi-threaded. So we use multiple threads, because you can really use the CPU we have only when you use multiple threads. And then next step would be multi-process. Multiple processes means that we need inter-process communication somehow. If it's on the same server, you could use named pipes if you want, but typically it's a HTTP call or some bus messages. Next step would be multi-machine to get more memory, mainly, because one machine typically has enough processing power for business applications. And at the end, the last evolution step is auto-scaling. That means that instead of having a fixed number of nodes, the number of nodes depends on the current load or depends on some scheduling. So for us, that means at 6 o'clock in the morning, we scale up based on time because we know until 6, almost nobody is working in our system, and then people start showing up at work. We scale down during the morning, scale up again over lunchtime. And additionally, when the CPU load gets too high, we add additional nodes to the system. And when you go multi-machine, auto-scaling, please be aware of the fallacies of distributed computing. I won't get into that, but these are some things that we always forget when you work in a distributed system, and we are always surprised, although this is knowledge that was there for a couple of years already. And always ask yourself, how many concurrent users do I really have in my system? Because scaling is a fun topic, but I would say most business systems don't need scaling. Fast, single-threaded code would be enough. We aren't Netscape and Google. Next thing is about response times. So we have a web client that talks to our backend system and says, yeah, give me that data, do that for me. And at the beginning, yeah, we do everything that has to be done on this single request. In our system, for example, when you come to work, we call that the time booking. You say, now I work, so we store that in the database. Yeah, you started working, great, have a nice day. But we do a lot more, because when you add the time booking, we know that maybe your day is now correct or it is incorrect. Because if you come to work, you should leave also. Otherwise, it's not a correct day. And maybe you worked too much. You had too little breaks. Or there are dozens of rules that we apply on any given workday. So these rules have to be applied. And if we do it on the same request, the request gets too slow. So we started offloading these things. We write a message to our service bus, please validate this workday, and it happens some milliseconds later. And if there is a problem, you get the to-do to solve it. Another thing is fire and forget. Mainly we use that for reports. So if you want to report, you say, yeah, thanks for your request. You get an email when it's done. So we don't block the request. And the third thing is a strategy where you say, instead of having a single request, I use a bunch of parallel requests to get some data. I have an example for that. This from our applications, what we call a team widget. And there you see your team. If people are really working, yeah, at the moment only Gerhard is working with I can see it on the screen. No, only Hans-Rudi is working. Emma is on vacation. Tim has a birthday, and Hans-Rudi will compensate in the afternoon. So at first, we loaded that data. We said, okay, it's me. Please give me the data for my team widget, and we returned all that data. And that was really, really slow, because all teamers, when they show up, open the application, they all need a little bit different data. So what you did instead is, first request is, system, please give me the employees I have to show. So I get a list of these 5 employees here. And then, in parallel, I ask the system, okay, please give me the data for the first, for the second, for the third employee. And now what you can do is we can cache the data. Because If Emma requests the data and when Gerhard requests the data, they share a lot of employees. So we can use that cached data to return it quite immediately. And that's resulted in a much, much faster system overall, despite that we're having much more requests to the backend, because we can use caching of the same data. So I come to conclusions. I must be fitter than last Monday because I'm running 5 minutes faster than last Monday when I trained for this for this presentation here. But then it means you have a lot of time for questions. That's great. So conclusions is when you think about architecture, you have to acknowledge that you don't know that much about this problem and your solution. In 6 months' time, you will know a lot more. So if possible, if you can defer a decision, don't make it now, make it later when you have more knowledge. But of course, some things have to be decided now, otherwise you can't work. If you just add some features in any way, you will have an architecture, and it's better to have conscious decisions about the architecture than just accidental decision making. But try to solve the architecture problems that you really have today. But again, keep an open mind. Have a goal where your system should go. For us, it's mainly number of users. You probably have different architecture goals or product goals of your system. Make sure that you find a way how you can reach them. You don't have to know exactly how you will reach them, but if you have several options for a decision, choose the least risky one, the one that leaves as much options open as possible. So you don't have to refactor your architecture later. That will happen nonetheless, but less times, hopefully, than when you just ignore the future. So act now, but look ahead what's coming. And one good thing is to think about in scenarios. So we ask ourselves, what happens when we hit 10,000 users? What do you think now, what has to change in our architecture or in our system? And could we do that without having to change big parts of the system? The answer is yes, then okay, fine. Or we say, we have to introduce translations in 4 different translations. It's all Western European languages, so the UI can stay the same. You don't have, for example, if you have Chinese, you have to change the whole UI. We don't need that. Can we get there if we need translations? Yes, we can, but we have to make sure that if we have context-aware translations, for example, if you are a German user seeing data of a French person and you want the address to be rendered for a French person, so you have 2 different languages. Language of the user, language of the person you see the data. Think about such things, if you can handle that. If the answer is, yeah, we see a way how we could do that, again, it's fine. And because we have a little time, a classic is archiving data. Did you ever think about what will happen when you have too much data? The system gets slow and you have to get rid of some data. You want to archive data. Think about that in your team, because my experience is in most teams the answer is, oops, no, that doesn't work. And that's a bad answer. Again, you can take the architectural aspect slide ahead, the one with the many letters on it, go through these aspects and ask in your team, what would happen if something would change there? And yes, keep as many options open for as long as possible. So then I'm at the end and you have some time for questions. And you see, when you don't have questions, I have questions. Please.
This team member example, multiple requests, in order to be able to do caching, if you design it properly inside of the system, you still can do caching even if you have one request.
It depends where the cache is. I can cache the data, get one request, read all the caches, combine it into a single answer to the request. Yes, we do it with multiple requests. But you are absolutely right. Yeah, that would be also a possibility. Just take the one that is simpler. And our approach is fast enough, and you have to think about it, but I think it's a little bit simpler than doing caching in the backend. And I'm not sure. But that's an option, yes. Thanks for that. Please?
If you want to be prepared for the future, isn't there a big risk of choosing like the most general, the most complex architecture in order to be able to transform into more simple one? Or thinking about event sourcing. I mean, it could be that there is logging requirement later on, so you just choose to use something else.
Yeah, the question was, isn't it risky to think too much about the future, because then you choose a very general, probably too complex solution? And that's actually one of the main points you should take with you is, no, build a specific and concrete solution as you can for today. No configuration, not generalization, nothing, as specific as you can. But have a concept, know a way how you can change your code, that if you need to change something, that would be possible. So I have another talk, I gave that last year about simplicity, and that's also there, that go with the simplest solution that works now, but in a way that you can change it. Because, yeah, that's the typical answer is, yeah, maybe this comes and this, let's make it configurable, let's make it flexible, generalize everything. You end up with a code base that nobody understands. Yeah, good point. Thanks for that. Yes, please.
Can you hear me all right? Or should I say, what is, in your experience, which approach worked out better for you on the subject of the fallacy of distributed computing, preventing possible errors with sophisticated mechanisms like fault tests and circuit breakers, or do you think focusing on recovering from those errors is more beneficial?
The question was regarding fallacy of distributed system. In my experience, is it better to be, what was the word you used? Be resilient against failures, or to try to prevent them? And first, I would only distribute if I have to. It's the most important thing. So our system is more or less a monolith that runs on multiple nodes and uses Azure functions. So, but in the sense, it's more of a monolith. So we reduce the fallacies that can occur. And on the other hand, we want to be resilient against failures. And that's something where event sourcing helps us as well. If we have the same event multiple times, for example, it doesn't hurt us. So I think it's really hard to prevent. So if it's easy to prevent one thing, yes, do it. But overall, I would say preventing stuff is really hard, and you are never really sure if you really, really prevent it. So it's better to be resilient against problems. So we had one funny thing is, that's not in the, I added that to the fallacies of distributed system, is clock skew. So you have multiple nodes, and the nodes don't have the same time. So you can guess, attendance time tracking system, time is really, really important. And we found out that a couple of years ago that our nodes had time difference up to minutes. 3 minutes was the one that our telemetry showed. Yeah, these nodes differ by 3 minutes. Don't ask me how that is possible, but it was the case. So it happened that events got had the wrong ordering because they took the time from the node. Of course, you had to change that and pass the time always around. It's always the better idea, but yeah, bugs happen. So that was one that was really hurting our system, clock skew between nodes. Yep. Is there... Yep, okay. Is there another question? If not, I have... Oh, I switched the slide. Let me go back. If you meet me in the hallway afterwards, and I look you in the eyes, I want you to answer me both those questions. What did you take away from my talk? And what did you like best? And if you're really, really nice, answer these two questions and send me an email. I would really, really appreciate it. Because the feedback from the conference always, yes, your talk was 4 out of 5 stars. Yeah, it's nice, but I can't do anything based on that feedback. And as you have seen, I value feedback a lot. So please talk to me afterwards. Answer these two questions. I would really appreciate it. Thank you for your time and have a nice rest of the conference.